Yeah, my name is Daniel, and I'm going to present Proofviz, an interactive visual proof explorer. So let's say that you are an undergraduate and you're taking a course on theorem proving. You just covered induction. You want to prove this theorem that, if you add two numbers and add one to the result, it's the same as first adding one to one of the numbers and adding them together. And remember from course that we use intros to bring names from the bottom to the top. And we just covered it in class, so we probably should use some form of induction here. LMN seems to work nicely. The first case is pretty easy to deal with. We're on to the second case. We have names on the bottom again that we want to bring to the top. And remember the implementation of add-in pattern matches, so we should be able to automatically simplify this at least one step, which for some reason that doesn't work. But we can write out what we know the simplification will be, and then rewrite using that. And we can see that we can use F equal here because we have the induction hypothesis that works without some extra S's, and then it will hold with the S's. The exact details don't matter, but we can use that tactic and prove the theorem. So pedagogically, this isn't the greatest way to prove a theorem. We don't really have a good intuition about what's going on under the hood. We want to see what is the proof term that's actually being generated here. So, tactics, they're great because we can automatically track the proof state. They allow for some great automation, but it's really opaque, especially if you're a beginner and you don't have any intuition about what's actually being done with a proof. We're just kind of moving things around. We don't know what's actually happening. All right, so then what if we did the opposite? We start from the bottom up. So for example, in the little typer, we start with a dependently typed language, and then we build proof terms constructively, only focusing on the proof term. So, nothing's hidden. We can really see what's going on in the proof term. And then, these are just regular values. We can use them as part of other proofs. And, this is great because it's very transparent, but it becomes quite unwieldy. It can be somewhat hard to follow this proof, especially if it's just presented on a page. When we put these two proof strategies side by side, it's hard to believe that they say the same thing. How are they connected to each other? How do you get from this tactic proof to this actual proof term? So we can see that there is a correspondence between each part of one proof with each part of the other proof. So for example, this F equal tactic corresponds to the congruence constructor here. Or when we call a lim, that corresponds to this induction term here. Again, reflexivity corresponds to this same constructor for equality. Even intros corresponds to these lambda binders in the finished parts of the proof. So, these bottom-up proofs, it's very explicit, and you can see what's going on, but it becomes very verbose. And the style works well when you introduce the proof over the course, of a full book chapter. But if you just have the proof written out on the page, it can be kind of hard to follow what's going on in this proof. So I wanted a tool to make this really explicit to me. And so I didn't really find a tool that I wanted, so I made one and call it Proofviz. And so this is sort of what it looks like. Let's go through each part in a bit more detail. Just the raw proof term itself. We'll get to exactly what each of these different nodes of the tree mean in a moment. Then in the middle column, we have information about the currently selected node of the proof tree. So we can see the context, which is what variables are accessible at this point in the proof. We have a goal, which is what's the type of the term that we're expecting here. And then the rest of the middle column depends on what the exact kind of node in the tree. So for example, this node that's selected is called an apply node. It has any number of subterms, and then it substitutes in a concrete value for each subterm into a finished piece of syntax. So for example, here we expect a subterm that has this type, and then once we have a subterm, it will substitute it into this lambda here. So again, for this specific node, we do have a complete subterm for that. And so this is the result after substituting it in. Lastly, we keep track of which tactic generated each node of the proof tree. So this node was generated by the intros tactic. And this is pretty persistent for the rest of the proof. Then on the right-hand side, here we have some interaction with the proof itself. So we can enter new tactics, and we can step through proof using an undo and redo functionality. So we can see what's going on under the hood of the proof tree. It's very explicit. But it was built on the Kerr theorem prover, which itself was created using the Racket macro system. It operates using dependent types. And what's nice about Kerr is it's very extensible. We can run a whole bunch of different experiments without needing to modify the core language of Kerr. So the tactic system, for example, was created without modifying the core. You can add experimental type systems with size types. You can integrate with external tools such as solvers. And in this case, we have a proof visualizer that we were able to create without modifying the core language of Kerr at all. So how do we use this? Well, so a tactic in the NTAC tactic system is modeled as a function just from the state of a proof to a different state of the proof. So we have a function or tactic display focus tree that accepts the current state of the proof. It pops up a window showing the proof state and all that. And then once we close the window, it will return the state of the proof back to the rest of the proof script. We can also use, instead of the NTAC form to declare, the start of a tactic script, we have an alternate form, NTAC/visual. So at first glance, this seems like it just inserts the display focus tree tactic at the end of a proof script. However, if we have other tactics in the proof script, it will collect information about the state of the proof between each tactic and fill the undo buffer in our proof visualizer with that tactic. So this means that we can use the same tool both to develop new proofs and to explore existing proofs and step through them. So if we start with an empty proof that has, we're trying to prove the same thing about adding two numbers and adding one. And let's run the intros tactic. We can see that we added a few nodes to our proof tree. In this case, just a few lambdas and context nodes. So this node here is focused, meaning that any tactics that we apply will be applied to that node. We can change the node that is selected without changing the focus. So any new tactics will still be applied to this focus node, but we view information about this selected node in the middle column. So if we look at this, we can see, again, we have our expected subterms and the result that we substituted into. At this point in the proof, we don't have our concrete term with the correct subtype. So all we have is just saying when we do have this subterm, this is what it will look like. And we have the tactic that generated this node. We run our induction tactic, and we can see now that we have more stuff in our proof tree. Here we have two holes, the base case and the inductive case, and the base case is currently focused. So if we look at like this new limb node, so at this point we have our n and j variables in our context, we have our expected goal type, and we have now two subterms. These will just get substituted in to their place in our result. So here, new lim is a generalized eliminator for any abstract data type. So there's a little bit more boilerplate than the specialized ins and at from a few slides ago, but so it will just, but this will, when we substitute in the subterms of the correct type, it will give us a term with the correct goal type. And we would see that this node was generated by our induction tactic. Let's select the other hole, the one that's not focused. And we can actually change the focus using this tool. So if we click that button, it will change the focus, and it will generate a navigate tactic. So what this does is when we close the window, and it will print out the proof script. So this navigate tactic allows us to, it will change the focus in the outputted proof script as well. So that way, any tactics that are applied there will be applied to this new focus instead of our original one. Let's undo that and go back to where we were before changing the focus, though, and apply the reflexivity tactic. So this will generate the literal term reflnat sj, which has our expected type here for the base case, and this would be filling the hole. Now this whole subtree would be considered complete, and we move on to the next hole that's focused now. Then we run f equal to handle the congruence, and this again just creates a function, or it creates a piece of syntax that will call the f equal function with whatever subterm we generate that has this expected type. And then we can actually see we have in our context a name that has that expected type. And so we can use that. We can just use IH3 in this case as our term to fill this hole. And so by assumption, we'll do that. And we could see now IH3 is the literal syntax that's used to fill this hole. The other thing is, so this, we were just stepping through the proof with undo and redo. We could have also typed in a literal tactic itself and it will have done the same thing. So visualizing tactics using a tree structure is not a new idea. So for example, PVS came with a visualizer where you can lay out the tactics in a tree based on how many sub-goals are generated. And this was re-implemented in Proof General later on. And this has applied to other theorem provers as well. However, you can't really see the proof term here. It lays out the tactics, but it doesn't solve the issue of seeing what's going on under the hood of the proof assistant. Similarly, you have the sequent visualizer. So you have a more mathematical view of how each step builds on later steps, what's assumed in each step, and then you need to prove those assumptions. And again, so this is useful in that context, but it still doesn't show the relationship between the tactics and the proof term that those tactics are generating. This is a slightly different, so more recently you have software like Electron, this solves a slightly different problem, and that is just proof scripts being a bit opaque. So this will insert the intermediate states of the proof into a generated markup file. And so again, it doesn't solve the exact same problem, but it's worth mentioning just because it speaks to the same need to make proofs a little bit clearer as you're going through them. And so lastly, in proof general, you can see a point-in-time representation of the proof object with the various holes. However, it doesn't associate parts of the proof object with a tactic. You need to manually call it each time between each tactic. So it's not very ergonomic or discoverable for new users. In terms of how this can be extended in the future, we can integrate better with the IDE for Racket, Dr. Racket. So for example, instead of needing to call ntac/visual for every proof that we want to visualize, you might be able to have an IDE button that does that. We can have a tree diff view before and after a tactic. So we already keep track of which tactics which nodes of the tree are generated by each tactic. So this wouldn't be conceptually hard, it would just need additional GUI work. So currently after closing the window, we just print out a list of tactics in the undo buffer. It would be useful to be able to save that to an existing file. And so sometimes some of the nodes can be a bit redundant. It's useful for the machine as we're going through each proof, but some of the nodes might be a little bit extra if you are looking at it visually. So just a way to hide those would be ergonomic. So just in summary, it allows us to bridge the tactics and the proof terms that those tactics generate, which is especially useful for beginners to tactic-based systems. It allows us to develop new proofs or visualize and step through existing scripts using the same tool. And we didn't need to make any changes to the core of the proofs assistant to get this to work. Thank you, and looking forward to any questions.
Let's thank our speaker with a few claps here, please. And I would like again to encourage you to raise your hand to ask questions so I can invite you on the stage. And if you can't raise your hand, then write your questions in the Q&A section. Okay, so we have a raised hand by Grigori, or Georgi, I'm sorry. So let me invite him on the stage.
Hi, thank you. It's Cryo for short, or George, anyway. So thank you for the presentation. It's been a long time since I attended university, so I was wondering what level of student is this aimed at, and is it common now to use this kind of notations actually in proofs? Because back in my day, it wasn't that common.
So this would be aimed at someone who is learning the fundamentals of dependently typed languages and wants to extend that to real world proofs. So instead of just building like toy programs of dependent types, how do you prove simple but real things with these? And that's where proof systems start to be useful.
Right. So this is kind of a specialization, not main track, maybe in mathematical logic course or something like that. Just to put it on the map for me.
Yeah.
Okay. Thank you. Yeah.
Okay. Peter. Oops. Peter, you're on.
Yeah, yes, I can see myself. Hi, Daniel. Thank you for your presentation. I also put it on the Q&A tab. I'm not sure if you can actually see that, but there's a suggestion for related work. By work has been done in Nijmegen by Maarten de Mol. if you Google for Sparkle and Maarten de Mol, I'm sure you will find a hit. So there was also publication CEFP 2007, and the reason I'm bringing it up is that a lot of the original motivation of that work really is very similar to yours. So trying to visualize both the term on one hand, but also having access to the tactics that you want to apply to that term. The context is slightly different because it was targeted for functional programmers in Clean. So the idea there was, can we prove properties of real Clean programs? So your area is slightly different, but I do think it's really worthwhile looking at that bunch of work.
Yeah, I haven't seen this before. I'll definitely look at this after the talk.
Okay, thank you.
Thank you.
Other questions? Well, I'll ask a question while we wait for somebody else to raise their hand. Do you have any experience in how useful this is to actual users or students in assisting them in actually developing a proof?
We haven't done any user studies yet. I found it like personally useful developing some simple proofs just for just for demonstration. However, we haven't done any user studies yet on other undergraduates.
Okay. It'll be interesting to see the results, right? So
Yeah.
please keep us up to date with your progress.
Thank you.